Okay, hello everyone. I'm Geeta Hudson, part of Dakshina Chitra, and we're very happy to have Dr. Vijay Shankar to speak to us on a very unusual subject, at least for even artists like me, I've not heard of. He has his PhD from IIT Chennai in chemistry, and he's done some very interesting stuff. He is a material characterization expert. I got to hear of it for the very first time. Basically, it's about the effects of different lights and stuff like that on different materials. And it's about aging art, and it's about linking art and science. And it's also about the most important thing is about art conservation. And he's passionately involved for the last 15 years, and this whole talk is about Raman Spectroscopy, which is C.V. Raman's, the Nobel laureate for his work, and I'm very curious to hear more about it because he said he's going to speak for the layman. He's going to explain the scientific part for all of us, in a language we all understand. And as an artist, I'm very keen to listen to his talk, and we welcome you once again. And thank you all for joining in today. And yes, please, sir, Dr. Vijay Shankar, you can go ahead.
Thank you, madam, for your introduction, and also vanakkam, swagatam, and very good evening to everybody. I wish you all a happy and a safe stay in this pandemic. And thank you for all of your time to have assembled to listen to me. Before I start, I have two requests. One is like, since you're seeing me, I'm just stopping my video to save the bandwidth. Second thing is like, if you feel that it's too scientific for me, just interrupt me. Okay, I would like to make it more lucid, and the content, I make sure the content what I intend to present reaches you better. Okay. So as you've heard, so today I'm trying to give you some useful applications of Raman spectroscopy to be used in identifying some intricacies as well as some secrets behind the art, and as well as to use it as a tool to conserve or to find out the aging and other degradation process. Okay, so what I have planned is like to just give you like what this Raman spectroscopy is basically. Okay, so before that, you might have heard Sir C.V. Raman being the first Indian and the only Indian till now to have received the Nobel Prize for his beautiful invention of this technique. So let's start with how Raman got intrigued that resulted in his discovery, and eventually it led for his Nobel Prize in 1928, 1930, and he published this discovery in 1928. So we are kind of 90 years of celebrating his discovery. And ironically, this year, I think a couple of months back, Raman even went to Mars. Now he is roaming in Mars, which is true in the sense like the first ever Raman spectrometer was sent along with the rover in the Mars to know about the details of life is present or there, or to identify what kind of minerals, what kind of geology is present in the Mars. So I'm really happy to share this technique which we can use in Earth for our own art and art conservation. So it all started when he was coming back from London to Bombay in SS Narkunda ship. So he was just having a small piece of nickel prism in his hand, and he was very passionate about this light scattering. And that time Lord Rayleigh was doing all this work in London. So he was puzzled to see that why the sea is blue. because we all know that when you take the same water, sea water in a glass, it doesn't look blue, right? So we were all thinking, or we were even till now. I mean, to the best of my knowledge, many people would say like, why the sea is blue? Oh, it's reflecting the sky. Sky is blue, so the sea is blue. So then, why the sea doesn't turn yellow, orange, pink, or whatever the evening hues, right? So the same question 90 years back, Raman had in his mind, and he tried to say that if this is reflection, and if I see the sea surface from the ship using a polarizer, he can cut off some reflections, like the polarized sunglasses we use right now to reflect the glare. So then it would appear black if it's a reflection, but it was still looking blue for him. Then he understood, no, there is something beyond this. Okay, so he immediately made a note of this, and he discussed this before he could land in Bombay. He put a mail in the ship itself. He sent a message to Lord Rayleigh that Professor Rayleigh, this is what I observed. There is something different what people normally think. So that's how the technique of Raman scattering started. So after he came back, he then moved to Calcutta, where he was working as a professor in Indian Association of Cultivation of Science. People who have visited that place or who are from that place still can go and see the small wooden spectrometer he fabricated by himself in ISCS. So what is Raman effect basically? So I'm just telling in a very layman's language. I'm not going to go deep into what is the science behind it or what is the instrumentation and other thing, because we are mostly going to be looking at the applications, right? So I'm just restricting myself to just a couple of slides and a 2-minute video to you. So it's simply a light scattering technique. Whatever any molecule, any material for the sake, liquid, solid, gas, all the 3 states of matter. When it interacts with light, it scatters a part of a light. So this is a simple explanation of Raman effect. So, but the trick here is there are 2 things. If you can see in the right-hand side image, there is a light hitting a molecule, which is nothing but water. So the 2 gray balls are hydrogen, and the center red ball is oxygen. So it's just a water. So what happens when water interacts with the light, visible light? I'm not talking about any very high funda light or anything, electromagnetic. It's a simple visible light, because that's what he observed in the sea. So when it just interacts, there are 2 things happening. One is whatever the light that is hitting the molecule will be just coming out scattered in all possible radiation without any change in its character. In the sense, light is always associated with color. Scientifically, it is called as wavelength. Wavelength means it will have a frequency. So these 2 combinations will give you energy for any radiation. So without any change in anything, it just comes out. It is called as Rayleigh scattering. But what Raman found was there is some part of the light that is scattered, but whose wavelength is bigger than what the light was sent to it. That means the wavelength is high. This is what he found. And the interesting part is how much of this wavelength is scattered is 0.0000001%. It's very, 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 very minute amount of light that is scattered from the molecule or from the material for the sake of convenience is different from what it was taking inside. This is called as Raman scattering. So I'll just restrict up to this point. So this is what the whole crux of what a Raman scattering effect is. So how do we see this, right? So I say it's 0.6 zeros next before 1. How do I really see this, right? So he discovered, he set up a various like detectors to even see the very weak intensity light. And he found that when laser light, when a visible light goes through water, it emits a light around 3000 to 4000. centimeter inverse. This is the unit. Forget about it. Okay, like how wavelength is measured in meters or centimeters and nanometers. The typical unit here is centimeter inverse. So he found this is. So this is how a typical output of a Raman spectrum looks. On the y-axis, you see the intensity. That means how much intensity has come out. And in the right, in the x-axis, you will see what is the wavelength or what is the wave number, which we call wave number in this case. So that is the unit of the wave number is centimeter inverse. Okay, like sometimes when you see our ECG or report, we don't understand anything, right? So it's the same thing, but here I'm just explaining what is the x and y axis, as simple as that. So how big is this Raman instrument? So how complicated is this? Definitely, it's very simple. To the right, whatever you are seeing is the pocket size Raman spectrometer. You can just take it in your pocket and go. If my pocket is little big, okay, it's something a size of half the size of your iPad, honestly speaking. And when Raman did this, there was no lasers. He was able to work only with the brightest source of light. At his time was the arc lamp, the Mercury arc lamp. That was the brightest source where cinema projectors and other flashlights used to use. So he did that. But after that, there were so many technological innovations. Now laser has come. The main advantage of using laser in this Raman technique is like laser is highly intense, very monochromated in the sense like the wavelength is very, very sharp. If I say a particular wavelength of light is 500 nanometer, yes, it's 500. Whereas in visible light, if you take, there are 7 colors involved with this, right? So monochromated light means it's just a single color light. And the intensity is very, very high. Obviously, the percentage of Raman scattering is also very high, and it's very easy for us to detect. So this is the simple construction of a Raman spectrometer. To know like how really one can see this Raman effect in the water, I'm just playing this 2 minutes video to you. Just let me know if you can able to see this video. So for brevity, I just stop here. So you have seen that I passed a green laser light into just a pure water, and without any filters, I could not see any Raman scattering. But if I put a filter that can cut my green light, I can definitely visually see the Raman scattering, which is a red light. So if you see this spectrum, whatever I am showing here, the wavelength of the red light falls in this region, 3000 to 4000. So this is the Raman. Now, where or how do I use this in art and conservation? Like what kind of information I do get when I use it? Because Raman spectroscopy is something like only scientists use, only laboratories, people who work in research only use. No, not that way. It's a very, very useful technique. In the sense, it's a standard now to use a diamond. Without Raman spectrum, you cannot identify whether it's a diamond or not. To know, I'm just giving you a very like convenient comparison with the diamond. To the right, you can see is a cubic zirconia, right? It's nothing but American diamond in our local language, which looks very similar to uh, this thing, as well as your the so-called Swarovski crystals. So whatsoever these are really the crystals are kind of zircon. It's a zirconium oxide. It looks very similar to diamond. Visually, I would say 100% people can easily be duped. But whereas a Raman spectrum of this simple crystal will give you two different spectrum of this material. So in the top, you can see diamond, which shows only one sharp peak around 1300 wave number. Whereas for cubic zirconia, American diamonds, Swarovski or whatsoever the case it is like this. And if you take for glass, definitely it's going to be something else. So Raman spectrometer is a basic tool in any diamond industry. If you people who are aware of the diamond polishing and cutting industry in Gujarat or somewhere in Mumbai, each and every table has one small Raman spectrometer. They just check what is the purity of it. Not only this, it can identify whether the diamond is synthetic or natural, because there are synthetic diamonds you can create in a very small crystal sizes in a laboratory with high pressure using simply from carbon, because we know all diamond is nothing but a three-dimensional pure carbon material. So this is where Raman's application is really great. And any people who work in gemstones, like there are so many gemstones we know, precious, semi-precious, right? Like ruby, emerald, or some semi-precious stones like turquoise, tourmaline, amethyst, blah blah blah, so on and so forth, right? So everything, if you analyze in a Raman spectrometer, it will have its own spectrum. So what do you mean by spectrum? So like what is its own spectrum? Means it's like the Aadhaar card of that material. It's like a fingerprint of that material. There cannot be two same fingerprint, correct, in the world. Same way, there cannot be two different spectrum for a same material. And since the Raman spectrum can identify diamond very clearly, C.V. Raman was in actual extending this technique to find as much as properties of diamond. And basically, he is fascinated by diamond also. He was a great diamond collector also. Not many people know, but he's a very great diamond collector. And he had a lot of diamonds collected with him, including some from the royal families and other things. Okay, so this tells like how Raman spectrometer or spectroscopy, the technique is useful for a common man. That's why that's the purpose. If any scientific invention is not useful to the human actually, then it doesn't deserve any Nobel Prize. So that's why he was awarded the Nobel Prize. I think now we have seen enough about Raman spectroscopy and other thing. So what else it can do for art? So this is a very interesting story. There was an art gallery in New York Metropolitan Museum near to that. It was called as Nodular Art Gallery scandal. People who are involved in this should have come across this story. It's a very famous story also. The Nodular Art Gallery was established in 1846, and there was a guy called Peihian Qian. He was a Chinese who was living in Queens borough of New York, and he used to sell paintings which exactly looked like a replica of very famous painters, including Jason Pollock. Jason Pollock, I think people who are in this field might have known him, because he's a kind of famous for his abstract pictures by pouring the paint and then pulling the threads, strings, and something. He creates different patterns, which was very mesmerizing, and it was very highly valued. So what this guy used to do is he used to very technically replicate his paintings, and he used to put some vacuum cleaner dust, tea, and other things, so that it looks a old like masterpiece, something like that. And he used to sell it to one more broker. I forgot his name actually. So he used to sell that to the Nodular art gallery for millions of dollars. But this poor guy was equally very skilled enough, I should say, because any forgery person is equally skilled as the original person, because he could exactly replicate the original thing. Anyhow, but we cannot say both are same. So this guy was getting some few thousands of dollars. Then at a particular stage, some people got really doubt of it, and then it was checked by Raman spectrometer at that time. I would say around 2010 or around. What they found was in a particular the piece of art, they could find a pigment in one of the creases in the paper mesh itself. So that they checked, and it happened to be a pigment called red 170. This is the pigment he used. Of course, it's a organic pigment. It's not a kind of mineral based pigment. The funny thing about this is until Jason Pollock death, it was not available commercially that time. So he had procured it somewhere very specifically, and he was using his for his paintings. So this unraveled a kind of a great multi-million-dollar forgery at that time, and eventually there was a FBI case file. And since this patient Kian was having a dual citizenship, both in United States as well as in China, then he fled to China, and as per 2014 information, now he is living a very low profile, quiet life in, I think, Shanghai somewhere. I think he is no more selling pictures, but he's still painting. And that's how Raman spectroscopy has become a kind of very handy tool for whomsoever in art conservation, museum, and curator kind of jobs. Okay. So what exactly then Raman does is not only this to find out forgeries and other things, it can give a lot of information. Like sometimes we do not know with what technique a particular art or the masterpiece was created, what kind of pigments they use, what kind of base they use, what kind of final finishing, lacquer, and those kind of things. Or what kind of brushing techniques they use, what kind of like whether it's canvas or so on and so forth, right? So all this information can come from a single technique. And second thing is like it can authenticate like a masterpiece. So based on what pigment. So if you know what is the pigment, and if you know what is the age of that pigment, then you can say how old it is, and you can also find about like to whom it belongs, whether this particular dye or this particular pigment was available at that time or not, because fake sometimes look very original. I heard a story that when there was uh, a competition, who can act like Charlie Chaplin. So even Charlie Chaplin himself went, and he was not selected. So the fake looks more original sometimes, but nevertheless, original is always original, which carries a different value, right? So that's the power of Raman spectroscopy. And because of this, Raman spectroscopy is widely used in forensic science. People who are in forensic science will find it very useful because the instrumentation is very cheap, and you just need two lasers. And now so many diode lasers have come, because even people play, or we play with our cat with a small red laser, right? So there are so many lasers: blue laser, green laser, red laser. So it's very cheap. I think you don't need more than 2 lakhs or something to build a very like luxurious Raman spectrometer. So that's the like advantage of having a Raman spectrometer. And the main thing is like about using a Raman spectrometer, you can identify the age of a painting, or whether the painting is aging or not. We can do both. Whether it's from the cave painting, rock painting, Neanderthal times, medieval times, or even the contemporary like Van Gogh, or Guggenheim museum collections, all these things. Yes, all museums, all curators who want to really like have the authenticity and have a fingerprint on it, of a fingerprint of the particular masterpiece, they definitely use Raman spectroscopy. And so now it all depends on art means color. Either it is black or gray. Black is also a pigment. White is also a pigment, right? So how colorful was our past really, if you look at, because art is something it originated as long as from the Stone Age and Neanderthal time. We can even see some paintings in the caves also. So art born with the human race itself. So there are two kinds of pigments basically you can find. One is inorganic pigment, which is basically mineral based or chemical salt based. And another one is the organic pigment. Organic pigments are kind of synthetic dyes. Synthetic dyes. So these are natural, but nevertheless there are some chemicals synthesized in a laboratory also or in a like bulk scale. Okay, so basically it is two types. One is inorganic content, inorganic type pigment, and another one is organic type pigment. So if you happen to see in our food and in tablets or in our medicines today, there are so many colors, right? Tartazine yellow, brilliant blue FCF, titanium dioxide. So all these are pigments, just pigments. And some of the like junk foods or the fast foods nowadays we eat, they don't even tell what is the pigment or what is the chemical they use. They just say some code numbers. Red 102, blue 505. Right. So we do not know even what exactly it is. But nevertheless, all these are chemicals. That's the truth. So these are a few old pigments that has been used in kind of Egyptian painting or Afghanistan or Persian kind of those things, Mughals and those kind of things, and even including Mayan architectures and other things. These are some of the pigments they have been used in. And these are the colors that they were giving, and they are mixing this up according to their taste and whatever the color they want to finally get. And the main now the anything you want to see in white is nothing but titanium dioxide. Even in some of the donuts it is used. Okay, so don't worry about it. It's still safe. That's what people consider. And it's a $13.2 billion market now. It's going. So we are daily having it in our toothpaste, talcum powder, and so on and so forth. And even our walls are painted with titanium dioxide. So I said like Raman Spectroscopy can identify pigments. So this is one simple quick example for you. This is a painting of Saint Velgefortis by Anonymous Bosch. There you can like focus your spectrometer on any part of the painting and you can identify which pigment gives what kind of finish and what kind of color to you. So this particular painting is a medieval painting which says that the red color comes from calomel and kind of cinnabar. Cinnabar is nothing but mercuric sulphide, HGS. Okay, that's the chemical formula for it. Calcium oxalate. The mineral name is bedellite. So it's on the external layer, and there are some lead source also they could see because maybe like it has been used as an oil because they have to disperse all this pigment in those days. So linseed and those kind of oils have been used in those area those days, right? So that's how it can tell what kind of pigment they have used and how many layers are there and all those details you can definitely find it out. There are two ways to use this technique. One is like if I get any luckily any small piece or any small speck, even a small micron size particle is also fine. Or sometimes you can take the Raman probe itself or the laser itself to directly to the huge neurons or somewhere there directly you can take it on the spot and you can scan it. So both are possible. That's the beauty of this. And for micron size pieces or something something falls off during renovation or during degradation also, you can collect it. And if you just add a optical microscope zoom lens to the spectrometer, you can focus a particular part of painting and you can focus on that micrometer small speck. Even a small dust-like speck is also okay. It will give you the spectrum of what chemical it is or what pigments they've used. Uh, when I was making this presentation to you, I was desperately looking for many. Is there any studies that have been done on Indian art and culture? But honestly, I should admit that it's very sparse. It's very, very sparse. Very, very few are there, and one or two research publications I could see, but it was challenged by a consequent publication from somebody else. So what I see is, I mean, there should be a big awareness of this technique to be used in art and conservation, and equally, people should be made aware of the scientific richness of this technique. So that's what I feel personally. But nevertheless, there were like couple of analysis that has been done using Raman spectroscopy, and this is one such analysis I found. I think this was taken from one of the Chennai museum. That's what they have reported in that finding, and it's Rani Durgavati's portrait, approximately done in the time of 1560. And there they have found out at different places and colors what kind of pigments they have used. So one identification was like for red color they used typical pigment called massicot. Forget about the formulas because in nowadays it's easy to identify what is the chemical name of pigment. Okay, but for the sake of scientific richness, I'm just putting the formulas there. So those who are not aware of the what I say the chemical symbols, just read the pigment name. So for red, it is called as a red lead. It's a lead-based oxide, which is called as massicot. That was used there. And another place was where the area E, the marked E in the frame in the border was cobalt yellow. So this is one pigment, but the spectral signature is also slightly overlapping with another compound called studio red. Okay, but when you look at the age of the painting, which is 1560 AD, but at that time, the so-called pigment of studio red is not available because these pigments came later actually. So they had a doubt. That means this painting has undergone a renovation. This is where Raman comes very handy. So if I want to renovate, am I using the same pigment what the original pigment used, the original artist used, or am I trying to cover up with my own available pigment? Because some of the pigment may be obsolete now and it's very difficult. For example, one of the pigment that is used in this picture is called as Indian yellow, which gives a kind of pale yellow color to any paintings, which has a very funny history to it. It's obtained from the urine of cow or camel, and the cow and camel should be fed only with mango leaves. So people who are artists should have a cow or a camel, and they should feed only with mango leaves, and they should collect the urine and then dry it to get this particular pigment. So that's how it is there. So tomorrow, if you see a signature of tartrazine yellow in some of the picture that looks very similar to this kind of painting, then obviously yes, you can authenticatively say that it's a forgery, or some people have renovated it or touched up it. This is one of the reason I many times I'm very like interested to see there is a program in History Channel you might be aware of. There is a program called Pawn Stars, right? So there people used to come and sell the artifacts, old thing. They say no, this is from the Second World War era. This is that is that. Somebody has signed this. This painting is 1,000 years old and something. But how to really see the authenticity, right? So there are some experts used to come and find and see. But for the sake of brevity or for the footage, they just say like, oh, he just sees with the lens and says, yes, it looks fake, this looks original, this is renovated, this is touched up, so its value is less. But when it comes to a art piece like this, the value is somewhere, I mean, we cannot even match that, right? So this is where Raman spectroscopy is really handy. And to the right, if you see, this is the typical spectrum at different areas. It gives different this thing. Now here a question comes: will all the pigments give a good Raman spectrum for me? Will it be very giving a very clear fingerprint for me so that I can clearly identify? My answer would be no, because most of the pigments is also capable of scattering too much of the incident light, which is called as fluorescence. You might have heard this word called fluorescence, right? That means if you shine light onto something in a dark, it glows. It's a kind of glowing phenomenon. So most of these pigments, whether it is organic or inorganic pigment, this will try to glow when a light falls on it. This glowing fluorescence phenomena is brighter than or more intense than the Raman scatter. So it basically masks it. But nowadays, the technology is so high that you can completely cut off this glowing or the so-called fluorescence phenomena. Okay. So to know what fluorescence looks to you, if you see the profile B in this picture, it shows very weak peaks. Okay. And it's a kind of huge hump. This means the particular pigment is fluorescing. One good thumb rule here is like most of the inorganic pigments do not fluoresce. This fluorescence is very typical to the organic or synthetic pigments people who use post 18th or 19th century. Okay. So nevertheless, now there are so many techniques. One such technique, advanced technique, is mixing a small amount of silver nanoparticle, which is basically colorless. So it doesn't spoil the painting or anywhere. So what they do is like they just put a very like micro quantity of silver nanoparticle at that place, and then they do this Raman spectroscopy. So what this silver nanoparticle does is like it enhances the Raman scattering so that you can avoid this glowing or the so-called fluorescence. Okay, I don't think I want to go more technically onto this, but nevertheless, now the technique is so advanced, and Raman spectroscopy can overcome easily all this fluorescence phenomena. And moving ahead, this was one some interesting painting I came across where Raman spectroscopy was used. This is a picture drawn in 1887 by the famous American painter Winslow Homer. He named it as "For to be a Farmer's Boy." This is now in the Chicago Art Institute. When people look at this picture, it's a watercolor paint, and but they are a little confused because the whole environment, what the message that is coming out of the picture is in a sunset. But then, if it's a sunset, everybody say it's a sunset. Then why the sky is very pale? So this was the question people was like asking to themselves, and maybe that is what created a kind of curiosity, and it was giving a different perception to the viewer. But what the truth really is like when this particular water paint was analyzed, there were some of the areas little red lake pigment was found in the paper. Red lake is a kind of pigment that gives a red, and when you mix with blue, it can, or when you mix with some other lighter component, it can give you a shade of the dusk. So originally it was having, the sky was having something like purple to the typical shades we see, during the sunset. So that was there. So this tells that this picture has undergone degradation. Normally, people who are into art conservation know that it's very difficult to conserve a watercolor art. Not every time you can put it in display because of fading or bleaching by light. Whenever you want to show it for a very few hours only, not too much of lighting is there, or on a particular occasion you can show, and then they keep it back inside a dark, right? And it has to be preserved properly. So this is a particular application of Raman spectroscopy that tells whether the painting is the same as it was when created. Right. So this tells that it has undergone a degradation or bleaching, because some of the colors and some of the dyes even the ancient people used are susceptible to pollution attack, acid attack, moisture attack, and other things, right? So this tells like what kind of methodology we need to adapt to preserve its nativity. Now, this is one example where this blue pot is very famous in Jaipur. Even there are some traditional families who still continue this as a business. Basically, this blue pigment is kind of that has come to India through the Mughals, where when they had the interaction with the Persians and Afghans and the Turkish people. Okay. And when I just try to understand what this Jaipur tiles is, like it's specifically made with Multani mitti, Saji. Saji is nothing but our soda, washing soda. Okay. And then some typical gond, tree resin, they get in the their local area. And then it is mixed with quartz and indigo. So this is how it is done basically. Okay, so you can definitely, and it has that blue color coming from Azurite. I'm sorry, it's not indigo. I'll come in that next slide. So they used Azurite. Azurite is nothing but a mineral. I think in one of the slide I showed you Azurite is a kind of copper carbonate based salt, mineral salt, which gives you this blue color. Okay. But nevertheless, like in Indian context, blue means only indigo. We never used all these things. So this tells like what is the pigment, what is the technique we used in our paintings. Equally, like I tried to find out any studies that has been done on our famous Ajanta Ellora paintings, but there were some analysis done on that, but not using Raman spectroscopy. They were using some X-ray techniques that was giving them some information about the pigments they used. Maybe at a later point I can give you the reference. You can read that. Okay, but this one is particularly from Azurite, Azurite blue. This Azurite is particularly coming from the Turkish area, I think. And later, to make this blue color, people started using ultramarine. Ultramarine is nothing but a kind of sodium salt, which is naturally available, which was better bright blue than this copper oxide based blue. And recently, now we get cobalt based blue also. Cobalt blue has become very common. You might have heard typically this cobalt blue based glasses where the big cathedral chandeliers have used that. Okay, because it's easy to blend in making glasses. But nevertheless, cobalt is a heavy element and it has its own associated toxicity and other things. So these are some of the pigments, especially that gives blue color. Ironically, if you see that there is always a connection between Raman and blue, because when Raman saw the blue color reflected from the sea, that created all the next consequences, and he was able to identify this whole technique. So I thought like I would give a little emphasis on blue. Okay, so there are so many blues you can see: Azurite blue, Cerulean blue, Chinese blue, Egyptian blue, lapis lazuli, lazurite, manganese blue, Mayan blue. Mayan blue is indigo basically. Indigo mixed with a particular clay. Okay, and then they do a small heat treatment, which makes it acid resistant. It's a very like unique technique nobody has used before. So Mayan civilization has found this, and there is something called Windsor blue, which is a phthalocyanin blue, which came in the later 19th century, around 1936 somewhere. And there are so many other blue. Prussian blue you might have heard, but Prussian blue now is synthetic. In those days, it was from the natural salt they were getting. And there are so many and so on and so forth. Vanadium blue, cobalt blue, and so many. So now the question comes, if I say blue, there are so many blues I listed. So how blue is my blue? Well, blue can have different shades. Okay, light blue, dark blue, cyan blue, greenish blue, grayish blue, bluish blue, blackish blue, right? So many blues can come. But nevertheless, in those days, getting a blue color was very, very rare, really rare. The only available source was Turkish blue, which is Azurite, Egyptian blue, which dates back to ultramarine and other things. Chinese blue, I think they used cobalt salt and something. So, if you see the medieval art in anywhere in Europe or something, only very few unique pictures will have this blue color. Not many pictures will have blue color because it was not available that time, and it's very difficult to get also. So you cannot see much of blue over there in any of the medieval paintings you find in Europe. So most of this blue color was restricted to Egyptian, this Persian, like Turkish, Afghanistan, as well as some in India. Okay, and this is one typical Raman spectrum that has been done on one of the Egyptian painting. It has a very typical signature. So definitely this would say if somebody uses some other blue to create the same kind of effect like Peking Xian, we can definitely say it's original or not. Now comes what is Mayans blue. I told right, Mayans blue is made with indigo, the natural plant extract, and mixed with a clay. To be honest, and in those days, BAS of the German-based company was trying to make indigo by in their factory actually. So for that, they spent like the amount of money they spent was something like more than the worth of the company itself. So blue was such a rare, and it was considered something like blue is a royal color, right? So there was a craze for blue basically. And this is a typical example where Raman spectroscopy has been used on this Mayan art. I think this picture is from the Quetzalta pyramid, where they could see this particular kind of, and there are many such pictures. And this tells there are at different areas. What they did, like they took clay, whatever they used, the clay is still available. So they were comparing. So all these 1, 2, 3, 4 are the signatures, Raman signatures of various components like clay, then this particular indigo, then indigo just mixed with clay, then indigo mixed with clay, and then heated. Right. So they tried all these things, and one is the direct spectrum from the mural itself. So it tells like, yes, this is the combination. So today, if I want to like restore this picture, then I will know what are the ingredients, how to mix it, what will be the shade I will be getting, whether I am authenticated using any authenticated way to restore or not. Okay, or otherwise I can buy any like synthetic blue paint also I can do this, but it doesn't match with the quality with which with the originality. Now comes the blue, the real blue. This he is our Chennai guy, Subramaniam. So he is the guy who taught us to make holes in the ozone, because he is the man who is having close to 100, 150 patents for inventing the chlorofluorocarbons in DuPont when he was working. So, but he was at one stage of his project in Oregon State. He got a funding from the National Science Foundation of USA to make some superconductors. So he told his student Andrew Smith to make some indium oxide, manganese, and yttrium oxide. Okay, to do some superconductor. But what he got was a bright blue powder oxide, but it was not a superconductor. Okay, so if you are new to these names, whatever I'm saying, indium oxide, manganese, and yttrium, don't get worried. Indium oxide is the main component of any touchscreen you use in your mobile phones and other things. Manganese oxide, any brown bottle you see nowadays is manganese oxide based. Yttrium oxide is nothing but it's mainly used in the tooth crowns nowadays. Okay, so yttrium oxide, zirconium oxide mix. These are used in making the people who go for root canal after they put a crown, right? So if you go for a very little high hard material, so that you can easily eat whatever the hardest food possible. That is made of yttrium oxide. And this particular thing was called as imine blue. Okay, based on indium, yttrium, and manganese. So YN, YIN, Mn. So yttrium, indium, manganese blue. So this was something a kind of revolutionary serendipity, because for past 200 years there was no much blue pigment available, and this was the first ever synthetic inorganic based blue pigment. And looking at this bright blue thing, one of the company in Australia called Shepherd Color Company bought this technology, and now they are using it. And whatever now it has been licensed to many companies. Even the Crayola you use for this bright blue, okay, is having this in blue. Then in blue has become a kind of pride. So many people started using, many companies started using it. Many people started using it in their CD covers, DVD covers, and other things. So that's how the man behind this in blue is Subramaniam. He is called as M.A. Subramaniam. So it is called as mass blue. So in Tamil we say Nalla mass katitampa. So he is really a mass man, okay, when it comes to blue. So now comes like where I can use Raman spectroscopy in archaeology. This is a very, very recent study that was published in collaboration with Vellore Institute of Technology. One of my friends is also working in this technique. So you know about key area. I don't need to much explain about it, but just to give you a flair of like where and what it is. The civilization is roughly somewhere between 6 BCE to 3 CE. And close to 6,000 artifacts of Iron Age civilization has been excavated there with a typical Tamil Brahmi inscription. And this is kind of created a kind of, what you say, a revolution in the human civilization also. Anyway, but this is a beautiful finding in our own state. So what is unique about this is, like you can see the potteries, right? Like with black and red color. What is so unique about this black? And second thing is, they were not seeing the black in the outside of the pot, but in the inside of the pot, and it was very shining also. And even after several years, it was buried inside, it didn't degrade. So they were really puzzled, like what really it would have caused, like to get this kind of black pigment, because nevertheless, black pigment till date, the minute I'm talking is only carbon based. Any black color you get is only carbon based. Even my fabric, my thread, my cloth, whatsoever I use, plastics, wires, anything you see black is carbon black. Nothing is black without carbon. Okay. So what they found, they used a Raman spectroscopy. I mean, it's a kind of these shirts are like excavated, so they could get a fine little scrap in one of the corners, and this is the microscopic picture, and there are so many fragments of the black particle, and they check the Raman spectrum. Typically, if you take a Raman spectrum for any carbon-based material other than diamond, okay, I showed a diamond picture in the beginning. Other than diamond, if you take soot, graphite, the so-called new wonder material called graphene, and whatsoever the various types of carbon you see, you will see basically two peaks. One is called as the D peak, another is called as the G peak. G peak refers to graphitic peak, because if you take a Raman spectrum for a pure graphite, the conducting rods, whatever we use in any furnaces or even the old movie projectors, they used to put on rod, correct? That's a burning rod which gives the bright light. So that's a graphite rod basically. Or you, for the sake of your pencil, the pencil you use is a graphite powder blended with a clay, because graphite is very soft. To make it little hard, it should not break while writing, they mix a clay. That is what is called as highly bonded. That was HB pencil, right? HB means highly bonded. That means it is bonded with the clay. So that's compared, like it's nothing but a graphite. So if you just take a Raman spectrum of a graphite or your pencil lead, it will show two peaks. One is D band and G band. But what is interesting is there is a peak around 100. which is called as the ring breathing mode. Because if you look at what the structure of carbon there is, if it is a single sheet of carbon like a chicken mesh, it's called as graphene. If I roll it, it becomes single walled carbon nanotube. If I fold 3-4 layers of graphene, then it becomes multi-wall carbon nanotube. If I keep on stacking several layers of graphene, one above, one above, one above, then it becomes graphite. So that's how, if you take a graphite, you put a scotch tape, peel it off. You are basically, what you are doing is like you are taking few layers of graphene out of it. For this, there was a Nobel Prize given to the Russian scientist. Okay. So anyhow, nevertheless, the Raman spectrum of this shows this particular peak, which tells it's a carbon nanotube basically, and it's a single wall carbon nanotube. So how do they know really this? The old Tamil civilization, how do they know really? Or whether without knowing they made this material? Yes, for sure, because these technologies came off late in the 20th, 19th centuries, right? But they did this for a particular purpose. I do not know for what. And that study is still inconclusive in that because it's very logical that if a pot has been used for cooking, then the carbon would have got deposited from the firewood. So it's very logical to see the soot outside. Okay, but it's not a soot. And second thing is, this carbon coating is inside actually. So why did they use? For what purpose they used? And in addition to that, they also found some silicate and other things, so which clearly tells that they have used vegetative source as a carbon material like straws and other things now how we use. But this is a very interesting finding actually. And that's where Raman spectroscopy is very useful in case of this intricate samples. So this picture you would have really remembered now. This is the Last Supper. I was so lucky to get the chance of seeing this particular wall painting personally when I went to Milan a couple of years back, before the pandemic, of course. So this is in the Santa Maria della Grazie, and it's a huge craze to see this because it's the Last Supper. And what they did was like they analyzed this particular picture because this is a great masterpiece done by Da Vinci. So what when during the renovation, I think a small speck fell from Saint Bartholomew's part where I marked here. So what they did, like they took that small piece that chipped off from the wall, they impregnated in a polyester resin, because if it's a micron piece, you cannot hold it really, right? So to hold it conveniently, they just embedded in a polyester resin. I mean, these are typical methods used in microscopies. Okay, people who are into this in microscopy and other areas should know this. Or even if I want to take a small piece of needle and if I want to polish it, it's very difficult to hold. So it's best to embed in plastic, and then it's just the same way. What they did, they analyzed this particular sample using that Raman spectroscopy. But here a small change, like I told, there is an advanced technique in Raman which is called as surface enhanced Raman scattering, which is nothing but you just add a small invisible silver colloid to it, which multiplies your Raman scattering. So that's the technique here. So what they did, so this is a cross section picture. The scale bar is 0.2 millimeter. Okay. So they found 3 layers basically. The one is the wall. In between is the white lead. On the wall, first Da Vinci coated white lead, ground white lead. He readied the wall, and then he started painting. So the blue color, whatever Saint Bartholomew's robe, okay, is nothing but a combination of azurite, the typical inorganic pigment, and the ultramarine blue I told in those areas, because blue is very rare over there, I said. So one a very exotic picture, in a very little amount you will see this blue. And if you see blue in any European painting, people are really excited, that's why. So these are the two, but nevertheless, to have the shades really of the foldings and other things, Da Vinci was so intelligent to use 2 red pigments. one red pigment that is called as kermes red. Kermes red is nothing but kind of carmine red type, which is obtained from excuse me, from an insect called kermes vermilion. Okay, which was very popular that time to use to dye silk and wool. So any red color silk and wool is dyed mainly with kermes red. Then the carmine red came. Even carmine red is nowadays used in food coloring also, right? Which is basically an insect. And now there are so many red that has come. Naphthol red, red lake, these, that, blah, blah, blah. So many red dyes have come, but all are poisons, all are chemicals. So there are four Raman signatures you can see. The top two are two actual Raman spectrum done using two different lasers. Like I said, Raman always use lasers. You can use different lasers, blue laser, infrared lasers, what are the laser you want, because different lasers give different information, as simple as that. But the common laser is green laser. Wherever you go in any Raman spectrometer, you will see a green laser whose wavelength is 532 nanometer, or some people use 634. There is one more laser called 785, which is infrared laser. This is particularly used when the sample glows a lot. Like I said, there is a interruption in Raman phenomenon that is called fluorescence. To avoid the fluorescence, they use 785. And there is one more laser called 1064. It depends on where you use this. So forget about that part. Nevertheless, this is the top two are the real signatures from this particular blue area, and the bottom are the two reference, which is nothing but the direct dye you got from the insect. So with this, I come to the end of this presentation. I think I'm not like burdened you with too much of scientific things, but nevertheless, I try to give a glimpse of how Raman spectroscopy can be used in art and art conservation, archaeology, identifying the degradation, how to restore it, and other things. Okay. So it's a non-invasive tool. Definitely, either you can directly take the Raman laser and put it on the wall, or if you luckily get a piece, you can take it to your lab and put it under the microscope and see. And don't worry about the sample size. Even a small micron level sample is enough, where you can see the typical layers and everything. So this definitely is very advantageous. In this particular technique is called as micro Raman. That's it, because it's a Raman spectrometer attached to a microscope. So you can know what is the pigment, from where it has come, what is the time, whether it is from the rock age or from the iron age or the medieval time or the contemporary art of 19th, 20th century, everything you can find out just with a simple one spectroscopy. That's why now Raman spectroscopy is highly used in forensic science. So it can clearly identify even a small speck of sample from the what you say, the nail of a victim also. So if somebody is trying to kill somebody and there is a fight happening during the death, then a small speck of hair, all these things definitely you can. Okay. So, but as I said previously, my only wish is like this technique should be used more and more in the Indian context also, and there should be definitely collaboration between a scientific and this art and culture. That's where I end. Hope you enjoyed the talk. If you have any questions, you can please ask me.
Thank you very much, Dr. Vijay Shankar. Actually, you led us into a lot of insight into art preservation, copying, a lot of things which we heard of. We didn't know how people actually detected these things. And we also learned a lot about the blue, the indigo blue, and we even spoke about the red. So thank you so much for this very informative and the one which kindles a curiosity for future search on these areas. Thank you, sir. Thank you for your time and generosity. Thanks.
Hello, ma'am.
Yes. Parvati, do we
ma'am.
have time for questions?
Yes, you can have a couple of questions.
Yeah, the questions can go on, no problem.
Madam, I have a request. Like audience, when they are asking the question, please tell your background also. Because if you are accounts background and if you are interested in arts and science conservation, I can convey in a right way. If it's a scientist, yes, definitely I can converse in their language. So please introduce yourself, your background also in asking the question.
Hello, sir. I'm Ritvik from Dakshinapita.
Hmm.
I am here registered at Dakshinapita. So I have a few questions.
Please go ahead.
What is the intensity range of the laser we can use for detection?
It's a wonderful question. Normally, since we use lasers and lasers are very powerful, okay,
Yeah.
it tries to burn your sample.
Hmm.
Okay, so the experiment really needs some optimization. So you start with a very minimal laser intensity where you can really control. Okay, by controlling the microscope illumination or by controlling the laser power itself. Okay, so it's very easy. Just click of a mouse, you can do this. So you go with the minimum laser power to get a good signal to noise ratio, a good peak. Okay.
Yes, sir. And another question is, yeah. Another question is, can we detect like in many paintings, it is like artists they try to do it something, then they cover it with like another painting.
Perfectly, sir. Perfectly. I think.
Can we detect it? Can we detect it by Raman spectroscopy?
Yes, definitely. Yes, definitely. I think there was one specific example of this particular artist, Winslow Homer. There was another painting where he did something and then he wanted to change. I think one of the subject in that painting, first when he created, he kept the subject to be alive so that his hand was upright. But I do not know what happened. Like en route, he finished the painting. He wanted to make the hand look little drooped down, so he covered it up. That was also identified.
Yeah. For example, the first layer will it affect the result of the next final layer?
It will overlap because there might be some other pigment over painted on a particular area. Correct.
Yeah.
So, but nevertheless, you will see a mixture of signals.
Yeah. Okay.
Definitely, you can identify what. That's what I said. Like you can identify the secret of the artist. If
Thank
we
you,
do
sir.
not
And
know, if we analyze Mona Lisa, whether she was crying or smiling,
yeah.
that definitely you can say. Might be crying now. She is giving a charm smile. You can find it.
And if, for example, if a museum tries to find whether that means wants to do the Raman spectroscopy, and the museum do not have that facility, where that museum can approach in Chennai?
There are
Is
places.
there any organization or something?
Definitely, sir. You are close to IIT Chennai. IIT Chennai is a very beautiful facility of Raman spectrometers. You can either have a sample to them or you can approach the Raman spectrometer manufacturer who can build a facility for you to analyze on the site.
Okay, sir. Thank you, sir.
Yes.
Any more questions? Okay. Yes, there's one here. Parvati, can you read out the chat question which is there?
Yes, ma'am. So one person with the chemistry background, I've asked you, like, can you use Raman spectrometer for identifying building materials?
Definitely, building material in the sense like what era you are talking about. It's a concrete, or is it kind of limestone mortar based kind of thing?
He's talking about the Mahals of Madurai.
Yes, definitely, definitely. That's the mortar based construction. Yes, you can use. Definitely, you can use. And these are inorganic minerals. Definitely, you will get a beautiful signature of this calcium oxalate and calcium carbonate and other things.
Sir, one question here.
Please go ahead.
Is it a viable option to use this technology to identify whether a fabric is dyed by natural pigments or chemical pigments?
100%, madam.
In terms of cost
That's the
also, is
only
it a
technique
viable
available.
option?
It's very
Okay.
cheap.
Okay.
Within 2 seconds, you will come to know whether it is synthetic or natural. Because now all the Raman spectrometers has a
Okay.
built-in database. You can immediately, just in a click, it takes only 2 seconds to give you the spectrum. So online you can compare with, there are various database. There is a library of inorganic, synthetic, natural pigment database available. You can
Okay.
immediately compare and say, if I see something like I'm getting a post 19th or 18th century dye, then it's a synthetic dye.
Okay.
You can.
Okay. All right. Thank you
And
very much.
basically, you just need a few micron piece of that fiber, because one fiber is not more than 8 to 10 micron thickness, right? You just take one little, or you put the whole fabric under it.
Yeah. Okay. Nice.
And Sahana's asked you a question about does the field has it acquired its full potential today, or is there more scope for the several applications that you've been mentioned?
It's growing. It's growing right now. It's one of the handy tools anywhere you can see in any museums. Any museum and art conservation people use it. Diamond business people use it. Forensic science people use it. Of course, chemists definitely they use it. Like I said, like Raman has even gone to Mars. So it can identify whether life is there or not.
Thank you, sir. Does
Thank
anybody
you so
have
much.
any more questions?
Sir, just one curiosity, whether vermilion and cinnabar is same or it's different?
Both are kind of same, kind of same. Because see, vermilion is a kind of name given from the typical insect. Okay, right? So anything that looks red, they always say it as vermilion. Cinnabar is a more specific name.
So, cinnabar is like mineral name or?
Is mercuric sulphide.
Okay, sir. Okay.
In
Thank
Tamil,
you,
it is called as lingam. When you grind sulfur powder with mercury, little 10 minutes in a mortar pestle, you will get immediately mercuric sulphide. It's highly reactive, so it's cinnabar. I think there is one full palanquin full of cinnabar in the Mayan excavation. Actually, full of they found it. Very beautiful red vermilion cinnabar.
Okay, sir.
So if there are no questions, I would like to ask my question. I just need your feedback, like how you felt, whether it was up to your level or it was beyond your level. Please give me your feedback to me.
No, sir, it was absolutely fine because for people like me who know a bit about art conservation, this and that, but it was all very, it was a revelation on many aspects. Like we knew about, discovering fake in a very simple language. You explained how it is possible to, discover these things. You touched upon many things from diamonds to archaeological stuff and painting. So it was actually what do I say, we learned a lot.
Actually, like the one dissatisfaction me was that I could as much as examples from the Indian context. I really searched for it. There were very few studies that I think one of the few study I showed. But nevertheless, there are some studies that have been done on Ajanta, Ellora, or some typical rock paintings using other X-ray techniques. Okay, so if you see my title slide, there is a lady with a pearl earring, right?
Yeah.
So this is a very masterpiece of Vermeer. And
Yes.
recently, X-ray technique has been used to investigate this painting. And what they really was astonished was this lady, particularly when she was drawn by Vermeer, she was very meticulous in selecting the pigments to have a kind of makeup for her face. So it's a kind of how her face is glowing and how is lovely. So I think Vermeer know that time to use glow and lovely using various inorganic pigments. So that's a beautiful piece of work that has been done.
Okay.
So my thanks to Lalita Madam, Indumati, of course she's my sister anyhow. So very thanks to both of you, and thank you all for this beautiful interaction. And honestly, like Dakshin Chitra is one of my very favorite place in Chennai. When somebody asks me like where you want to go in Chennai, when somebody comes to visit Chennai, I always say don't go here and there, just go there. So that's one of my favorite places. I
Thank
love
you.
that.
Thank you, sir.
Yeah.
So yeah, we'll be in touch and we'll see how to bring you in for more lectures in the future when the museum really opens and becomes active
Yes,
again. We
and
will try and do
not,
some interesting program with you, sir.
yeah, don't hesitate to contact me for any kind of scientific assistance you need. Maybe like once I start to go back to lab, I have a beautiful Raman spectrometer with me. I can do some off the line help for you also.
Yeah.
I have beautiful microscopes with me, so since I deal with electron microscopes also,
Okay.
so I'll be happy to help you anytime. Always
Sure. Sure.
be in touch with me.
Uh, Many thanks, sir.
So thank you so much, madam.